All right. Can everybody hear me up there? Can you hear me? Can you hear me up there? Good. Since I gave a history of computing lecture, many of which you attended last week, I'm going to jump ahead to start talking about formal languages, which were founded in the 1940s. Could somebody also please pass a sign-up sheet? I'm going to take attendance today. Remember, attendance is a big part of your grade. So pass a sign-up sheet, write your name, your computing ID, and sign it. And pass it. So who wants to pass the attendance sheet? Like a couple of sheets of paper. Write your name, computing ID, and sign it, and start passing it systematically. And by the end of the lecture, I want all of you to sign your name, so you'll be credited for attending. And every couple of lectures, we'll do the same. Remember, attendance is part of your grade. I want you to get credit for being here. All right. So formal languages started in the 1940s after the work of Alan Turing. We'll get to Turing in due time, but Stephen Kleene was a student of Alonzo Church, along with Alan Turing. They were both graduate students of Church. And he invented regular expressions. The Kleene star, Kleene closure is named after him. We're about to define it in a few minutes. And many other theorems and formal languages, properties, and computability results were pioneered by him. And on the heels of that, Noam Chomsky, still alive, professor at MIT, he's probably in his late 80s by now, pushing 90, and he's a pioneer, a thinker, a intellectual giant. He basically single-handedly revolutionized the field of linguistics in the 1950s and 60s based on formal grammars. He started studying formal grammars to see how language, natural language, the languages we humans speak to each other with, can be put on a formal footing and studied symbolically and formally using logic and generating rules for producing valid, grammatically correct sentences and so on. And in fact, all of programming language theory is based on his work. The notion of parsing and grammars and context-free generating grammars and regular expressions, all the stuff the compilers do is based on his work. Lately, the last few decades, he's been a political activist, a dissident, and but he gets a lot of credit for pioneering the field of formal languages and generative grammars. So his so-called Chomsky hierarchy, which we'll study extensively in this course, in its basic form is this Venn diagram here, set containment diagram, and that's denoting the containments of certain classes of languages within other classes. So we have the regular languages, which subsume the finite languages, but also contain some infinite languages, and then the context-free languages contain the regular languages, but other things as well. And these green examples here on the right are examples of languages that are contained in that set, but not in the previous lower sets that are proper subsets of it. And then there's the decidable languages and the recognizable languages, and of course all languages are out here, and the largest class of possible languages. And we'll talk all about these sets and establish relationships among them and theorems relating their properties to algorithms and what can and cannot be decided about them algorithmically. A lot of the course will be about that. So many things are named after him, Chomskyan linguistics, Chomskyan models, and so on. And he's actually enjoying the title of being the most widely cited living scholar. He's most cited than anybody alive. How many knew that, actually? So If you count dead people, he's number 7 in human history, the 7th most cited and referenced person. And by the way, that includes Galileo, Socrates, Plato, and Jesus Christ. They're all on the list, but he's number 7. So he had a lot of impact on human thought, and the scientific world and the world of computer science, because those things gave rise to all of it. Here are some of the books that he wrote over the years. You can see sort of his political leanings. He talks about, U.S. foreign policy, not in a great complimentary way. Of course, nowadays it's easy to do. Failed states. He talks about certain administrations, like this one is about the Kennedy administration back in the 60s. Once Hugo Chavez, former president of Venezuela, got up in the United Nations and thumped on the podium a book by Noam Chomsky, which made it an instant bestseller, of course. He was complaining bitterly about, not the book, but about what the book says. So later, he was invited there. And once he had an interview with Ali G, before Borat fame. And he was a good sport about it. There he is, Ali G, fist bumping, with Noam Chomsky. If you want to watch a good video, watch this one, Manufacturing Consent, Noam Chomsky in the Media. He talks about how the media has a tremendous influence about everything we do, how we think, and about our politics and what we believe is true. But he didn't write it or say it recently. He said it 30 or 40 years ago. And I think this movie is probably from the 80s or 90s. So all this notion about fake news that you hear so much about, and foreign countries, taking over social media and throwing elections, he predicted that, and he talked about it decades before it actually happened. So it's a very insightful guy. Don Knuth, who's also a giant of computer science, he basically pioneered computer science in the 60s and 70s with his famous series of books, The Art of Computer Programming, said once about Noam Chomsky, he said, "I must admit to taking a copy of Noam Chomsky's syntax structures along with me on my honeymoon in 1961. There was a marvelous thing, a mathematical theory of language which I could use as a computer programmer's intuition." So that's how much street cred and homage he pays to Noam Chomsky. He influenced Knuth very, very directly. I'm not sure how Mrs. Knuth felt about him bringing that book along to the honeymoon, but still, pretty direct influences. There's even a cartoon on the web called Noam Chomsky and his dog Predicate. Your mileage may vary, but it's kind of cute and geeky, and both pays homage and makes fun of Noam Chomsky's contributions. And it's not to say that everybody agrees with everything he says, especially the political stuff, right? So he's very controversial in some circles and a hero in other circles, but either way, he gets cited and discussed and challenged or agreed with, and there's some dissenting opinions about his politics, but still very, very influential. So today we'll start with his work. And like I said, much of the course, the technical stuff of the course will be about that. So we're going to talk about formal languages, and then shortly thereafter about automata, regular expressions, computability, and how computation is defined and how it interacts with math and computer science, programming, logic, and all of it. So formal languages. An alphabet is a finite set of symbols. It's a set, not a sequence. There's no order, and it's finite. It's not infinite. Only a finite number of characters in an alphabet. Here's a simple alphabet. These green examples on the right here will track the definitions as examples. And by the way, if you have any questions, please stop me and ask questions. It's better to ask early rather than wait and until things are spiral out of control, and because things will build very heavily on previous things in this course. All right, a string is a finite sequence of symbols from that alphabet. Okay? So here's an example of a string from this alphabet, sigma, and usually we use the letter sigma to denote the alphabet. A language is a set of strings. Now it could be empty, it could be finite, or it could be infinite. but it's a set of strings. So remember the types very, very distinctly. Don't let the types get away from you, the types of the objects that we're dealing with. Okay. Maybe pass a sign-up sheet from this end too. It's going pretty slowly. I want to make sure everybody gets a chance to sign up the attendance sheet. So maybe start a couple of sheets from this end. Oh, it's already went that way? Okay, so maybe it's going faster than I anticipated. So we'll go with that, but make sure you sign it before you leave today. Okay, so a string length is the number of characters in the string. There's a weird spot here that I have to avoid. I'll try to remember that it's right here. Certain acoustical anomaly. Anyway, a string length is the length of the string, number of characters in it. The empty string is the unique string of length 0. There's no characters in it. It's denoted using an epsilon or a caret sometimes. And it's the identity element with respect to concatenation. So any string concatenated to the empty string, either on the left or the right, yields the exact same original string that you started with. String concatenation is defined as all the characters of one string concatenated to all the characters of the other string that you're concatenating with. So here's an example of concatenation of strings. Now, the concatenation operator can be extended to languages, and to concatenate two languages, L1 and L2, juxtaposition means multiplication, just like in algebraic scenarios. So the concatenation of two languages is simply all the strings of one language concatenated to all the strings of the other language in all possible combinations, all of them. You can't pick and choose. And of course, concatenation is not commutative. If you concatenate the other way, flip it around, you get potentially a different result. Just like certain mathematical operations are commutative and others don't commute, right? So addition is commutative, multiplication is commutative, but division is not commutative. And neither is matrix multiplication, for example. Okay, so string exponentiation is defined as raising a string to the kth power, which means it's concatenated with itself k times, right? And here's an example, a cubed is AAA. Any string to some power is that string concatenated with itself that many times equal to the power that you're raising it to. So exponentiation now is defined for strings. And language exponentiation similarly builds on string exponentiation. Raising a language to the kth power means concatenating with itself k times. So LL is L squared, L to the k is L times L to the k minus 1, right? So this is an inductive definition, recursive definition, where L to the 0 is simply the set containing the empty string. Not the empty set, but the set containing the empty string. These are two different things. Question? Do languages contain the empty string? Some do, some don't. It's just one more string. So some languages contain the string high and others don't. Some languages contain the empty string and others don't. It depends on the language.
So the concatenation of two languages doesn't necessarily have the elements that were in either language?
No, the concatenation of two languages does not necessarily have the elements of one language or the other. It depends if one of them has the empty string, and then they will. And even if they don't have the empty string, they may have some of the elements in one or the other. I should mark the floor with all the safe zones to occupy. Good question. More, yeah.
So for language concatenation, is it just the cross of all symbols in a set of languages, or is it the cross of all strings?
All strings, very important. Not the symbols. A string could be one of the symbols by itself, but that's just a coincidence. So it's very, very important you understand these definitions, because the entire course will be built on these definitions and other definitions. So let's clear up any misconceptions or ambiguities in this. And again, the handout on our website that says, notation and definitions, that 10, 12-page handout is very, very handy here, because a lot of these definitions are repeated there and explained there in one small place where you can always look up and easily find the definition. Any questions about any of these things? So for example, the language 0, 1, taken as so 0, 1 now is a language. Raised to the 32, what does that mean?
All possible, the binary representation of all possible integers that fit in the 32-bit.
Yeah, it's all 32-bit representations. all 32-bit strings of zeros and ones, all of them. How many are there, by the way, roughly? What's the size of this language? 2 to the 32, which is roughly how much in decimal? No, don't use Siri. Yeah.
4 megabytes?
It's about four megabytes, you see? It's 4, but not quite megabytes. Gigabytes, terabytes, exabytes, petabytes. Anybody know what any of these things are? Yeah, what is it? 4 billion, so 4 terabytes. So saying 4 megabytes, you're off by a factor of 1,000. That's like going to buy, you know, a latte and being charged $5,000 for it. That's how off that. So be careful. You know, as computer scientists, you should wrap your mind very tightly about orders of magnitude. Remember, I showed you that videos about orders of magnitude, the first lecture, scale of the universe, and in particular, powers of 2. Powers of 2 you should know in your sleep. So you should know that 2 to the 10 is 1,000, 2 to the 20 is 1,000,000, 2 to the 30 is 1,000,000,000, and 2 to the 40 is 1,000,000,000,000, and so on, roughly, and a whole bunch in between. That you should just rattle off without hesitation. You know, wake up in the morning and ask yourself these 5 or 10 questions about powers of 2, and you should not hesitate even for a second when you're groggy out of a good night's sleep, or right before you fall asleep because you're so tired. You know, recite your powers of 2. Very important. Any other questions about any of this stuff? Because things will build very quickly on these definitions. And a few more definitions. The reversal of a string is simply all the characters in the string written backwards, reversed. So it's another string that's the reverse of the other string. Language reversal are all the strings in the language, each one reversed, taken together as one big set of reverse strings, and that's the reversal of the language. Notice how these operators build on their smaller scale operators. So first we have an operator on strings, and then from that we build an operator on languages, which operates on each and every string in turn. And we did the same thing on the previous slide, right? We defined concatenation for strings and then for languages. We define exponentiation for strings and then for languages on top of that. So you see how the definitions and operators build on top of their simpler versions. They get overloaded to higher order types, to more complex types. Just like in algebra or math or arithmetic, right? You can define multiplication for integers, but once it's defined, you can define it for matrices full of integers, right? So multiplying matrices together involves doing a whole lot of integer pairwise arithmetic on the elements of the matrix, assuming the matrix is made up of integer elements. And then you can make multiplication on higher order things besides that, even beyond that. Yeah?
For string exponentiation, is W to the 0 the empty string?
So anything to the 0 is the empty string. I guess we didn't say that here, but that's true. And that's a good point. So he's extrapolating that W to the 0 is the empty string. How would you justify that? Why isn't it the empty set or nothing? Or why isn't it a zebra or my left shoe? Why is it the empty string? Yeah.
5 to the 0 is 1, so it should have our number 1.
Yeah, so exponentiation, even defined on integers or reals or other quantities, if you raise something to the 0, the answer is usually the identity element for that operator. What is the identity element? Something that once you hit the operator with that identity element, with some other element, you get that other element back unchanged. How many get that? Okay. So for string, the identity element is the empty string, with the operator being concatenation. So he inferred correctly that something a string raised to the 0th power will give you back the identity element and not something else, the identity element, of course, being the empty string. That's a good inference. Okay, what else? So we have language concatenation, and then language reversal, and then language union. So two languages unioned with each other are all the strings in one or all the strings in the other. Every string that's in either one or the other or both is in the union. So it's basically set union over all these strings that are the elements of these two sets. So again, remember, a language is a set. A string is not a set. A string is a sequence. Very different. And both are different in an ordered pair. And none of these are a matrix. And so keep in mind the types of the objects. I know it sounds straightforward right now when I say that. But I can guarantee you that in a couple of weeks, the types will be so compound and nested that you'll lose track of the type. And when you lose track of the type, you have no idea what the object that you're looking at. Even if you know the type, you may not know the object. But if you don't know the type, forget about it. Right? If you don't know that something is a mammal, you don't know it's a zebra. You have no way of knowing it's a zebra if you're not sure if it's a mammal. How many understand that? Because if it's a zebra, it is a mammal by definition. But if it's a mammal, it's not necessarily a zebra. So the type is much more important than the actual value of the object. And don't get me wrong, the value is also important. But if you don't know the type, you have no idea what the object is whatsoever. So language intersection, again, that's basically track set intersection. So a language intersected with another language is all the elements of one that are also in the other. So it's the intersection of the two sets being the two languages. Okay? Any questions about that? So it's pretty straightforward so far. Right? Language difference is all the strings are in one and not in the other. So it's like set difference. And here are examples. Here's an example of the intersection. Here's an example of the union. Right? Here's an example of a set difference. So if you take away B and D from A and B, all you get back is A. The D doesn't matter, and the B disappears because it's being subtracted out. Again, just like set difference, operators on sets, because languages are sets. Okay? And clean closure, that's the most complicated one we've seen so far. So L star is the language L raised to all possible finite powers, all the unions together. So now we build the clean closure named after Stephen Kleene that we talked about in the beginning of the lecture. Raise the language to all possible powers, because now you know how to exponentiate a language. That was one of the previous definitions. Now we're building on that. Raise it to the first power, the second power, the third power, the fourth power, all finite powers, all of them. Finite powers, not infinite powers. All finite powers. There's an infinity of them, but each power is finite. Each one is a language, which is also a set. And then you can union a bunch of sets together because union is defined up here. And we do that. So it's color-coded purple. You see, union is an or, intersection is an and clean closure is a bunch of ors, a bunch of unions. So I'm color-coding things. Pay attention to the colors. I took a lot of pains to color-code things properly so that things are more related to things that are close to them on these slides. I tried to be as consistent as I could in the color scheme. It's not arbitrary. So all the examples are green, for example, right? All these names of the operators are blue. Okay. I was very meticulous about that, very intentional about that for you, for your benefit. Okay, any questions about clean closure? That's a big one. That's a complex operator. It does a lot. All right? So if I take sigma being an alphabet, sigma being, say, A comma B, A and B, and that's the alphabet. Okay? What's sigma star? What's sigma star equal to? How would you explain that in English, rather than regurgitate this definition? Yeah. Okay, and is there a shorter way to say that in English? Every possible finite string made of A's and B's, which is what you said, but it's a little shorter, it's a little more self-explanatory. So it's any combinations of A's and B's, any finite combination of A's and B's taken as a string. How many understand that? Okay. Any questions about that? Now, let me ask you a couple of questions. First of all, L plus is all finite powers beginning with 1 rather than beginning with 0. So the difference between L star and L plus is simply the first element, the first term in this infinite union. Okay? So let me ask you a question. Here I'm stating as a theorem that sigma star contains no infinite strings. So sigma star here that we defined earlier contains no infinite strings. How many can prove that? How many think it has infinite strings? Okay. Well, I mean, I guess you better not, because I'm saying it isn't containing any infinite strings. So you're not going to contradict what I just stated as a theorem, right? But still, why is that true? How would you argue that sigma star contains no infinite string? And let me not be presumptuous. What is an infinite string? Just so we know what we're talking about very precisely. Yeah.
A string with infinite length.
A string with infinite length. A string that's so what's the last character of an infinite string? If I have an infinite string made up of A's and B's, first of all, can I have an infinite string made up of A's and B's? How many say, yes, I can? Yeah, sure. I mean, there's nothing stops me from saying it and you know, having some infinite sequence of A's and B's. I mean, pi has an infinite sequence of zeros through nines, past a decimal point, and there's nothing crazy or impossible about that, right? Even 5 has an infinite sequence of digits past a decimal point. They happen to be all zero. 5.0000. That's still an infinite sequence of zeros. So nothing stops you from talking or defining about an infinite sequence. But in this course, strings will have finite length. We'll not discuss or analyze infinite strings. They exist, and you can analyze them as a whole theory of them, but it's much more complicated, this scope of this course, and probably much to your relief, we will not deal with them here. So every string in this class will be a finite string of finite length. The length could be large, don't get me wrong. It could be a Google or a Googleplex or a Googleplex factorial, very large quantities, but finite nevertheless. Question?
I was going to try to answer what
Yeah, of course. What do you say?
since the star for operation is a union of each individual sets, and each individual set is contained of finite strings that contain an infinite string.
Yeah. So the first term here, L, what is L to the 0, by the way? L to the 0 is equal to what? The set containing the empty string. How many get that? How do we know? Well, we said it a few minutes ago. It's not the empty string, it's a set containing the empty string. That's very different. One is a string, the other one is a language. The empty string is a string. The set containing the empty string is a set, not a string, right? It's a set. It's not an animal, mineral, vegetable. It's a set. Be careful about types. So this is the language containing the empty string. L to the 1 is equal to what?
L.
Is equal to L, right? L squared is L concatenated to L. Right? But if you take sigma star, L is sigma. Sigma is a finite alphabet. In this case, say A and B. It could be other things, but it's a finite alphabet. And let's say it's A and B specifically. Then L squared contains only strings of length what? If sigma is A comma B, sigma squared contains strings of size 2. Yeah, size 2. L cubed contains strings of size 3. L to the 100 contains strings of only size 100, and there's a finite number of each. Right? How many realize there's only a finite number of strings of size 100 over A and B? Yeah, I mean, eventually you run out of combinations. Don't get me wrong, you get a lot of combinations. The 2 to the 100, that's a very large number, but it's finite. So each term in this sigma star, in this L star, where L is equal to sigma, contains only strings of finite length. The first, the second, the fifth term will contain only strings of finite length. The Google term will contain only strings of size Google, which is finite, big but finite. And so none of these terms contain strings of infinite length, and strings of infinite length therefore will not be in their union because it's not going to come of left field. It's going to come from one of the terms if it's going to be there, right? So that's a proof that sigma star contains no infinite strings, only finite strings, because no infinite string comes from any of the terms in this definition of the star Kleene closure operator, QED, end of proof. Right, question?
Is that the difference between L star and L, that L star can only have finite strings?
So neither one of them have infinite strings, right? L star starts with an L0 and L plus starts with an L1, but that's the only difference in the first term.
So the difference between L star and this L
Oh, I see. So he's asking, does L star contain only finite strings, but L may contain infinite strings? No, L will contain only finite strings also. If L contains Is this better? Yeah. Okay, so if L contained an infinite string, L star will contain infinite strings too. But L does not contain any infinite strings. L is a language is only a set of only finite strings. Remember, we will not deal with infinite strings in this course. So no language that we will deal with will contain infinite strings. You could define languages on infinite strings, but not in this course. It's too subtle, too convoluted, too far afield, and we're not going to worry about it here. Okay? So infinite strings will just not be in the scope of what we will do in this course, so you don't have to worry about them. So that's a blanket statement. I'm giving you like I'm doing you a big favor here by telling you that to you up front and then sticking to that for the rest of the course. So you don't have to wonder even. It ain't going to happen in this course. Although you could do it in theory in those forums where this is done. Yeah. Sigma is an alphabet, but you can interpret it as a language because it is a set, and it's a set of symbols. So technically, the characters are symbols, not strings. You can take a character, put quotes around it, and now it becomes a string. But technically, it's a symbol when it's part of an alphabet. It's a subtle distinction, but it's good that we nail it down very explicitly, like we just did. Okay, what else? Question?
Sorry, can you reiterate what the difference between L star and L is?
Well, the difference between L and L star. L star is L, which is this term, unioned with all other powers of L. So it's a lot more than L, right? It's L unioned with L squared, unioned with L cubed, unioned with all other powers of L. It's an infinite number of powers. And all of them could give you much different results than L. And they're all piled together as one big union. So L star contains L, but it can contain many things that are not in L because of this concatenation of L with itself repeatedly, exponentiation of L with itself. Does that make sense? It's like saying, what's the difference between 5 and 5 to the 7th? They're not the same. One is just 5, the other one is 5 multiplied by itself 7 times. Now, does that mean that x to the 7 is always different than x? No. Give me an example where x to the 7 is the same as x. X is equal to 1. So 1 is equal to 1 to the 7th. But that's just a coincidence. So L star and L could be the same, but they don't have to be. So if L is sigma star, L and L star are the same thing. Now we're saying that sigma star and sigma star quantity starred again, those are the same thing. But that's just coincidence. For that specific L equal to sigma star, that happened to be true. That L and L star were one and the same thing. Usually they're not. In fact, if L is finite, if L contains, let me make a statement. If L is finite, a finite language, is L star always infinite? How many say yeah? If L is finite language, L star is an infinite language. How many say no, there's exceptions? Okay, what are the exceptions?
L raised to 0 is a set of empty string, and that with that operation would still be a set with empty string.
So you're saying if L is the empty set?
Well, if it is a set with empty string, the language that contains empty string, and then use the closure thing, and it's still an empty string.
Okay, so basically you're saying that if L is the empty string and a couple of other things? No, just the empty string. Yeah, okay. So if L is just the empty string, L star is what? The same as L. Because you'll be concatenating the empty string to itself any number of times based on the different terms, and you always get the empty string, no matter how many times you concatenate it to itself, it's still the empty string. It's like all powers of 1 are equal. It's like all powers of 1 are equal to one another. But that's just a coincidence because we picked 1. But if we pick 2 or pi, all powers are not the same as one another. Right? Is that video camera still working? Yeah, all right. So if a language is finite, the Kleene closure, the star of it, is not necessarily infinite. Other than this case, is that statement true? Other than this example, is that statement true? That if a language is finite, the Kleene closure of it, the star of it, is infinite. How many say yes? Okay, how many say no? Is there another language that's finite whose Kleene closure is also finite, besides this one? So now we're exploring the definitions to see how tightly your mind is wrapped around these concepts and definitions. It's a good thing to do. What do you say? So here's a language where the only string is the empty string. Right? A string cannot be the empty set, but you're almost there. He's saying the language whose only string is the empty set. What is he really trying to say? He's almost saying it. Yeah, so the language that is, one word, empty. Right? So if you have the language that's empty, it contains nothing. Okay? Even the chalk couldn't hack this example. If a language contains nothing, it's an empty set, the Kleene closure of it is what? How we say the Kleene closure is the empty language? How we say the Kleene closure is the language containing the empty string? Right? We had votes. Some people voted twice. Can't be both. It's one or the other. All right, I'll ask again. If the language is the empty language, the empty set, the empty language is the same as the empty set. It's a set with nothing in it. There's only one such set. It's unique, the empty set. So if the language is the empty set, the Kleene closure of this language, the Kleene closure of the empty set, how many say it's the language containing the empty string? One string and it's empty. How many say it's the empty set again? Wow, we still have people voting both ways. Good, I'm glad I asked, because it can't be both. It's one or the other. Anybody want to argue one way or the other, which one it is? Yeah.
I feel like it's the same as the question, what's 0 to the 0? Because this empty set to the 1 or to the 2 or to anything is the empty set, right? But anything to the 0 is the empty string. And so we've got two different rules we've written for do this with anything, and it gives you,
Well,
and it's just a matter
okay, so here we have a case where it's important to know the definition, the precise definition of language exponentiation. You know, what is L to the 0, and what is L to the 1, and what is L to the 2. So if you're not sure what definition of exponentiation is at this point for all these terms, what should you do? It's pretty straightforward, not a trick question. What should you do if you're not sure about the definition of something? Go back and check the definition of that thing. I mean, it's not that hard to see that you need to go back and check definitions, right? So look at what we have on the previous slide. L to the 0 is the language containing the empty string. And by the way, why is L to the 0 equal to this thing and not to something else like an animal or a mineral, my left shoe, or vegetable? Why is it equal to that? Why would we define a language raised to the 0th power as this thing? Why not just define it as the empty language, or just the empty string, or a zebra? Yeah. So definitely, first of all, you need braces. Otherwise, it's not even the right type of thing. So a language is a set. It may or may not contain stuff, and if it contains stuff, you can debate about what that stuff is, but it's definitely a set. It's not an animal, mineral, vegetable. How many understand that part? Okay, good. So it's a set. So that's the braces. Now, why does it contain the empty string in there? Why not nothing? Why isn't it defined as nothing? Yeah.
So L to the 1 is the set of all strings with one element chosen from L, right? L to the 2 is the set of all strings with two elements chosen from L. L to the 0 is the set of all strings with no elements chosen from L, which
Oh.
contains one string, the empty string.
But if it's no elements, not even, maybe the empty string shouldn't even be chosen, right? Because empty string is an element.
But it's the string with no letter from out, with no string from out.
Okay. It's on the right track. What do you say? Yeah.
Oh, that is the identity element.
It's the identity element for language concatenation. That's a very disciplined reason why it should be that, right? And that reason tells you what many other identity elements are for operators that are applied 0 times, right? So 13 to the 0th power, what is that equal to? 13 to the 0. 1. Why not 0? Why not nothing? Why 1? Because 1 is the identity element for multiplication. Take a matrix full of numbers, raise it to the 0th power. What do you get back? Do you get nothing back? Do you get 0 back? Do you get 1 back? Do you get a zebra back? I'm not just being facetious. I'm trying to illustrate the point here. What's a matrix raised to the 0th power? What would you guess at this point? It should be. It's the identity element with respect to matrix multiplication. And what is that for a big matrix? Square matrix, let's say. Somebody else. The identity element for matrix multiplication is a bunch of 1s on the diagonal and 0s everywhere else. How many understand that or seen that? Oh, good. And why is it that, and not pi, and or not 0, or not an empty matrix, or not a zebra? Because it would be the identity element for that operator. So this is the identity element for language concatenation. Any language concatenated with this thing will give you the language back. How many see that? Because you'd be concatenating epsilon with all the things in the language, and that won't change them, because concatenate something with the empty string will give you that string back. So all these strings are concatenating a language with the empty string will give you that language back, each and every string that is in the language. And so that's the identity element with language concatenation, with respect to language concatenation. Okay, so we're taking a very systematic, disciplined approach to these things. We're not just guessing about them, right? So how did we get to that? Well, people asked, what is the empty language starred? So now, what do you think the empty language starred is? So if we take the empty language and we star that, what do you get back? At this point, it's not a trick question anymore. It never was a trick question, but at this point, it should be obvious, right? What do you say?
You're trying to imply that it is going to be an empty string, but my question is, wouldn't the L1 concatenated with L0 in this case not really make a lot of sense because you've got the empty string concatenated with nothing?
No, you're unioning them together, not concatenating. So the empty string union with something is that something. So that's okay, but you're right to worry about that. If it was concatenation, maybe it would be undefined or something. But you're concatenating the L to the 0, which is this language here, with other things, and the other powers, so already you have the empty string. And other terms will not give you any other terms besides the empty string. You're not going to get a string that says hello world out of the empty string concatenated with itself a bunch of times. Right? Where are these other characters going to come from, right? So, it would be that. It would be back to L here, which is the empty, which is, no, actually it's not L, it's this. So, okay, other than these two examples of the empty language and the language containing the empty string, if a language is finite, will the Kleene closure ever be finite, other than these two examples? How many say yes? How many say no, it will always be infinite? Okay, and that's right. As long as it's not one of these two pathological examples where it's either empty or the language containing the empty string, which are not the same as each other. One of them is cardinality 1, And this one has cardinality 0. This one has one string, this one has no strings. They're not the same language. But if you star them, you'd get the language containing the empty string in both cases. And that's the only two cases where the star of something is finite. If you have any other characters besides the empty string in the language, you star it, you get an infinity of strings right away. How many see that? Okay, good. Any questions about that? Now you see why we harped so much on infinities the last couple of lectures. The infinite hotel and Cantor's transfinite arithmetic, and the fact that integers are countable, and so on and so on. Because now a lot of the objects we're dealing with, other than just a few, will be infinite sets. There'll be languages which are typically infinite. Some languages are finite, but others are infinite. And all the interesting ones are infinite. So it's good to wrap your mind very tightly around cardinalities, infinities, orders of magnitudes, right? One-to-one correspondences, dovetailing, and diagonalization. We'll get a lot of mileage out of all of these concepts. Okay, any other questions so far? So sigma star contains no infinite strings because they will not come from any of the terms here in the definition, and so they will not come from anywhere, so they won't be there. Right? Just because there's an infinite number of terms here doesn't mean that any one of them gives rise to infinite size strings. Some of them give rise to a lot of strings, and some to more strings, but each one gives rise to only a finite length strings at each exponentiation term of this long union, infinite union. So the union is infinite. But just because something is infinite doesn't mean infinite things must arise from there. Just like that, a carrot is not going to come out of there either. Where is it going to come from? Well, where's an infinite string going to come from? It's not. And neither will a carrot. Right? So I'm not being facetious. I'm just trying to dramatically illustrate these concepts. Right? Okay, any other questions so far? So far we just had a bunch of definitions and a couple of theorems, simple theorems, and we're going to go deeper and deeper into this. All right, so next, language complementation. So the complement of language, sometimes denoted as L apostrophe or L bar. Sometimes we will say L bar as the complement, right? Like that, L bar for not L, or the complement of L. Are all strings that are not in the language. So now you know what sigma star is. All finite strings made up of characters in sigma, sigma being the alphabet. So the complement of a language is all strings that are not in the language. Subtract all the strings of L from sigma star. Because sigma star is all possible finite strings over the alphabet. Subtract from that the language itself, and that's the complement of the language. All things are not in the language. How many understand this definition? So it's the set complementation. Now, when you complement something, you have to make sure you complement it with respect to some known universe of objects. So let's, for example, let me show you how it can go wrong if you don't pay attention to the universe of objects with respect to which you complement things. So think about the prime numbers, right? Prime numbers aren't divisible by 2, only divisible by 2 or themselves and nothing else, prime numbers. So the complement of the prime numbers, how many understand what the complement of the prime numbers mean? What are the complement of the prime numbers? How would you describe it other than saying the complement of the prime? The composite numbers. So is 20 in the complement of the prime numbers? Yeah, because it's not prime. But is my right shoe in the complement of the prime numbers? How many say it is there? How many say it's not there? It's not there. But why isn't it there? It's not a prime number. My shoe is not a prime number. How many understand? How many agree with that? My shoe is not a prime number. So shouldn't it be in the complement? Complement is all things that aren't prime numbers. You just told me my shoe is not a prime number, so therefore my shoe must be in the complement. Where is this logic going wrong here?
It's like you said, we have to define our universe first, like our alphabet and the languages.
Yeah. You have to define the universe with which we're complementing against. So my shoe is neither prime nor composite. Primeness and compositeness is not even defined for a shoe. It's not even defined for a real number, never mind the shoe. Pi is neither odd or even. It's neither prime nor composite, pi. Neither is I, neither is a matrix, neither is a function, prime or composite. Prime or composite are properties of integers, in particular positive integers. And you can't just apply them to arbitrary things. And when you complement, you have to complement with respect to some circumscribed universe. And you have to be very careful about that, otherwise you get into trouble very quickly. So if you don't keep that in the back of your mind, this notion of complement with respect to something very well defined and specific, and something that makes sense with respect to type, you'll end up with saying things like, you know, my left shoe is a composite number, or at least not a prime number. And neither one of these statements that makes sense, because primality or compositeness doesn't even apply to shoes. And you know, I'm just bringing it to your attention early on, so you don't get into trouble over that when things are a lot more convoluted and subtle later on. Okay, and this is a theorem that L star star is equal to L star. If you star it twice, it's the same as only starring it once. That's true for any language, including these pathological examples here. How many can see that, or not necessarily be able to prove that right this second, but you know, it sounds believable. If you star it twice, the same as starring it once. Intuitively, why would you say that's true? Yeah.
So starting at one gave us every possible finite string made up of that alphabet. And starting at twice does the exact same thing.
Yeah, so if L is sigma, starting it once gives you all possible finite strings from the alphabet sigma. So starting it again will not get you any more strings than that, because that's already all strings that there are. So you're not going to get anything new. But that's, of course, that assumes that L is sigma. L may not be sigma. L may be the set of strings made up of the English alphabet, all English words made of strings. All the works of Shakespeare, each one long string. Like Hamlet would be one long string. And somewhere in the middle of that string will say to be or not to be, you know, and there's a whole bunch of other on either side. And so, you know, let's say the language is all strings that are the plays of Hamlet, however many dozens there are. So L star and L star star will be the same thing. But now, neither L star or L star star contains all possible strings, just concatenations of works of Hamlet. And that's definitely not all possible strings. Even Hamlet was not that prolific. Right? Yeah.
When you union like two identical sets, you're just going to get the original set. They're already
Yeah. So basically you're saying all powers of a language, that's the language star, all the union of all powers, if you star it again, you get more powers, other powers. But you already had all possible powers of the language with the first star. So any other powers obtained by raising something that's already a power of something to something else will get you just a different power, but all the powers were there to begin with. Anyway, that's kind of the crux of the proof. I'll let you flesh out the rest of the details. But that's a theorem. It's not a definition. It's a consequence of the definitions. So that needs to be proven, and we just kind of argued why that's true. Another theorem is that L plus is L times L star. That is more obvious, right? If you take L plus and you compare it to L star, the only difference is in the first term. So if you take L star and multiply the whole thing by L, all these powers will be clicked up by 1, and then you get L plus. How many see that? Because concatenation distributes over union. Just like in arithmetic, multiplication distributes over addition. So A times B plus C in parentheses will be A, B times plus AC, right? That's the distributive law. So it's a distributive law that you can use to your advantage here. Okay. So the trivial language, we already seen it, now we give it a name. So it's a language that contains only the empty string. That's called a trivial language. And the empty language, we already saw that over here. It's a language containing no strings. These are both unique languages. There's no other language that's the empty language other than this thing, and no other language that's a trivial language other than this thing here. The cardinality of the empty language is 0. The cardinality of the trivial language is 1. Okay? And that's one reason why they're different. Yeah.
I have a question about the second here.
Yeah.
So would that apply to the empty language as well? Because if you do the empty language for L plus, it doesn't contain L0 and the empty string. So there'd just be empty. But then if you do L times L star.
Oh, good. So if you apply this to the empty language, you get empty here, and that one would have the empty string. Yeah, that's a good question. For extra credit, resolve that one way or the other. I'll leave it up to you, but that's a very good observation. You know, he's asking whether this is true right here if L is equal specifically to the empty language. Good. And if it's not true, then we have to modify this theorem, right? To say this is true unless, or for all languages being not empty, for all non-empty L. I'll let you try to split that hair for extra credit. Excellent question. It means you're thinking about these definitions and their consequences. Other question, yeah, back there. Yeah. Yeah, so what he's saying is that if you apply this here and you concatenate all of these things, you concatenate L to L plus, and L plus will be the empty language. If you try to concatenate an empty language to something else, there's nothing to select from, and there's no possible terms in the concatenation because you have nothing to select from. So it doesn't matter what else you're concatenating to, you get the empty language. But what he said earlier is that, yeah, that would be an argument why this will be empty here. But he's saying, but this won't be empty, you know, by this reasoning here. It'll contain the empty string, and it won't be empty because there's one string in it, the empty string in the star, because the empty string will come out of the L to the 0. So still, having said that, let me give you a chance at extra credit to try to resolve it one or the other, but it's an excellent point. He's saying this theorem may have to be modified with a slight contingency, L being not empty. Okay, excellent point. Okay, more theorems. Sigma star is countable. Now, before we learned about infinities, we couldn't have resolved this, but now we can. Why is sigma star a countable infinity? Well, first of all, why is it an infinity? Why is sigma star infinite for any non-trivial alphabet, for any alphabet that has at least one character in it? So let's make it simple. Let's say the alphabet only has the letter A in it. Not even a B, just one character A, one symbol A. Sigma star is what in English? If sigma contains an A, sigma star is not a trick question. Yeah. Any finite string of A's. Is the empty string one of those? How many say the empty string is a finite string made of A's? Yeah. How many A's? 0 A's. Good. So it's there. So sigma star, A star, is all finite strings made of A's. Why is there a countable number of them, not an uncountable number? Let me not be presumptuous. What is a countable infinity? I know we talked about it last time, but it's a new week. What's a countable infinity? Yeah.
An infinity of the same size of the set of rationals.
Yeah, infinity of the same size as the rationals or the integers. You can count them, 1, 2, 3, 4. Is that true of any infinity? You can count the things? No, because in the reals we already saw you couldn't count them. And what was the argument for not being able to count the reals being therefore uncountable? What was the proof technique that we used? One word. Diagonalization. How many remember that? Diagonalization. Remember those two techniques, dovetailing and diagonalization. We'll get lots and lots of mileage out of them throughout this course, dozens of times. The answer will be diagonalization of dovetailing. Of course, that's the one-word answer. Then you have to explain why the answer is true, why the answer is descriptive of the solution. That could take a sentence or two or a paragraph, but it's nice to be able to answer a question with a single word. And why would I sometimes insist that you answer me with a single word? First with a single word, then you can expand your words. But why a single word or a two-word phrase? Why do you think I would sometimes say use one word to describe your answer? That's a meta question. it helps you focus on what's the most important aspect of your solution. Right? If you have to write an essay with only 100 words, it's much harder than using 5,000 words. How many understand that? It's just harder. Because you have to pick your words very, very carefully and focus on the most important words and be very thrifty in your succinctness of expression, and that requires a lot more thought, and it requires that you understand what's the most important aspects of this blurb you're going to utter for the next 5 minutes. Not all words are created equal in terms of significance and importance and their relevance to what you're saying. You have to cut away the fluff, which means you have to understand what the fluff is with respect to the important stuff, and that's not easy to do sometimes. Right? One of my favorite questions in a PhD defense, when a graduate student worked for 5 years and is about to present their work to the committee, to the PhD committee, and they have an hour to do this, one of my favorite questions to ask them is, explain to me what you've done in one sentence. Most of them fail to answer that question. They can easily tell you what they've done in 1 hour or even 20 minutes, but not in one sentence. They were never prepared for that. And in fact, they can't even do that unless they went back and thought about it really hard for a day or two or a week, and then they can come back and do it. But and how many see that's a really good question? How many heard of the elevator talk? What does that mean? You got 20 seconds to explain to a venture capitalist why you want $20 million from them, and the elevator door is just closed. And you're going up, and by the time the elevator door open, that person got to be convinced that you have an interesting idea. And if you can't tell this VC what you want the money for in 20 seconds and why it's cool and important and significant and potentially successful, goodbye to you and forget about it. How many have heard of that scenario? So we'll do this here. Somebody will say, in one word, tell me why this is true or what the answer is. And you have to be very, very thrifty in your use of words at that point, and forces you to focus on the important stuff. Right? And venture capitalists do this over money, and for very good reason. If you can explain your killer app in 20 seconds or 30 seconds, you probably don't understand it yourself. Or it's probably not that compelling. Take your pick. Either way, you don't get the money. So, sigma star is countable. One word. What's the answer? The 20 seconds is almost up. Dovetailing, yeah. How do we know? Well, it says so right here. The answer is even in front of you. So all you have to do is repeat what you saw. But more importantly, understand why that's the right word if you only got one word to say it. And by the way, why is it dovetailing? Now you can use a whole sentence. Why is dovetailing descriptive of the answer that the number of strings in sigma star, sigma being the letter A, why is that number of strings countable? You've got a whole sentence now. Explain dovetailing, how dovetailing would work. You got if the venture capitalist says, okay, you sold me on a 20-minute speech, 20-second speech, but now I want to hear the 20-minute version with all the details, you can't just keep quiet at that point. You got to be able to, cough that up too. It's not just the elevator talk that they want. That's the stuff that gets them hooked, but then they want to hear the rest. So what's the rest here?
So you can assign a discrete integer or value to each of the elements of that set going out to infinity.
Mm-hmm. And what would the value be for a particular string? Yeah, but let's nail down the value. So I have a string of 13 A's. What would you number that with? 13. Okay, but you didn't say that right away, right? So each string will be assigned the integer that's equal to its length. And now you're dovetailing through all the integers based on length. Now, if the alphabet has A comma B in it, it's a little more involved now. If the alphabet has two characters, A and B, sigma star is still all finite combinations of A's and B's. And what's the dovetailing now? And now you can use a full sentence. How would you number all strings of length, arbitrary length made of A's and B's? How would you number them with all the possible integers?
Same way you did the fractions. If you think about setting your A's and your B's in different directions, you would then traverse in a similar pattern.
Okay, but a string is not an A over B. It's A's and B's interspersed in some arbitrary combination. Yeah. Yeah. Sort all the strings by length. There's only a finite number of strings of size 2. How many of them are there? 4, right? AA, AB, BA, and BB. How many strings of size 5 are there? Of A's and B's. It's not hard. How many strings of size 5 characters, A's and B's, are there? 32, 2 to the 5th. So sort all the strings by length, and within length by dictionary lexicographic order. So AA will precede AB and so on. And you have a long list. Now just number them, 1, 2, 3, 4, 5, all the way down. There's your dovetail. How many get that? Okay. That's, you know, the one paragraph description of that one word, dovetailing. But when I say dovetailing, you know, you should sort of imagine all that. Right? Okay. Now, why is 2 to the sigma star uncountable? Now here, let's not be presumptuous at all. We know what sigma star is. What's 2 to the sigma star? Well, if you have a set S, more generally, what's 2 to the S? What does that denote? For a set S, 2 to the S is the power set. It's a power set. It's a set of all subsets. So it's a set of sets. So 2 to the S is the set of all subsets of S. It's not equal to S. S is one of those subsets as an element with braces around it. But there's other elements, there are other subsets of S, and all subsets are there in 2 to the S. How many get that? Okay, so you've seen that notation before, the power set notation. Sometimes it's spelled like with a capital, you know, P parentheses or whatever, you know, P of S, where P is this script big P. But that's okay. Here we use 2 to the S to denote the power set of S. And the reason we use 2 to the S is because the cardinality of the power set, if S is a finite set, the cardinality of the power set is equal to what? The size of the power set. How many elements are in the power set? The cardinality of the power set is equal to what as a function of the size of S? 2 to the cardinality of the set is the cardinality of the power set. How many get that? Why is that true? Somebody prove it. In one sentence, let's say. Give you a sentence, not a word. Yeah.
So when we form a subset, every element in the set is either in it or not in it. So there are 2 options for every element.
Yeah.
So 2 times itself, 1
Yeah.
for every element, 2 to the...
Exactly. So you take an element, you can either take it into the subset or not take it into the subset. There's 2 choices for every element, and a subset for every element will either that element be in it or not be in it, and there's k elements, so there's 2 to the k different combinations of yeses and nos, 1 per element, right? Being or not being in the set. End of story. Right? So the cardinality of the power set is 2 raised to the cardinality of the set itself for finite sets. How many understand this proof? Okay, any questions about that? That's important. Okay? And it turns out, for infinities, it's also true in the sense that in a transfinite arithmetic sense. In particular, the cardinality of the power set is bigger than the set itself. Always. For finite sets, that's true, and it's true for infinite sets, too. So now we know what 2 to the sigma star is. What is 2 to the sigma star? It's the power set of sigma star. How would you describe in English 2 to the sigma star, therefore? What does that mean? It's only 3 symbols, but it's a very convoluted, heavy notation, expands, to a huge degree in terms of the object that it yields. Yeah, and that's a mouthful. So sigma star is all possible strings over the alphabet sigma. 2 to the sigma star are all subsets of these strings. So it's all languages over the alphabet sigma, where a language is some arbitrary set of strings, each string coming from the alphabet sigma, made of characters coming from the alphabet sigma. So 2 to the sigma star is a set of all possible languages, all finite languages, all infinite languages, and every other language is in the power set also as an element, not a subset. So 2 to the sigma star has a very compound type. A language is already compound. A language is a set of strings. A string is already compound type. What's the type of a string? A sequence of characters. So that's already compound by saying it's a type of another type. So it's a sequence of characters. A language is a set of sequences of characters because it's a set of strings. So we just said that a string is a sequence of characters. So a language is a set of sequences of characters. So what's the type of 2 to the sigma star? Just the type, not the actual value for a particular sigma. Now I'm waiting. Is it an animal, mineral, vegetable? What's the type of 2 to the sigma star? You see, we're up against potential type errors already. And it's already, it's just the beginning of formal languages here. It's going to get a lot worse. So I'm asking for the type of 2 to the sigma star. How many know the type? Yeah, just a few of you. What did I tell you? How did I know this was going to happen? Because it happens every single semester. I've been doing this for longer than you've been alive, and this happens right away. The type gets away from you. And like I said, if the type gets away from you, you have no idea what the object is actually. Because if you don't know it's a mammal, you have no idea if it's a zebra or a horse or a mouse. Because if it was any one of those things for sure, it would automatically be a mammal. So if you don't know the type of 2 to the sigma star, you have no idea what it denotes. I'm just saying. So let's nail down the next 2 minutes. What's the type of sigma star? It's a set. A set of what? Of strings. And what's the type of a string? A string is of what type? Everything is a type. Yeah. It's a sequence of characters. Good. So sigma star, its type is a set of sequences of characters. So it's nested 3 deep. A set of sequences of characters. It's like in programming, you have an array of pointers. And each pointer can then point to other things. It's a compound or a nested type, right? You can have an array of records of pointers to websites. That's a nested compound type. It's not just an integer or a real. Right? So the type of sigma star is a set of sequences of characters. But what's the type of 2 to the sigma star? Again, it's not that hard of a question. I just want somebody to say it and say it correctly, at least once. Yeah. It's a set of sets of sequences of characters. It's nested 4 deep, the type. How do you understand that? Okay. So all subsets of sigma star will be there in 2 to the sigma star, each one as an element. So wrap your mind very tightly around that. Now, why is that uncountable? You can prove that by diagonalization. And I'll leave it up to you as an exercise to prove that 2 to the sigma star is not countable. Yeah, it's infinite, but it's a much larger infinity than the integer. It's like the infinity of the reals. It's uncountable. And try hard to solve that one. And in the book, we're about to enter we are entering chapter 1, finite automata, and next time we'll pick up with finite automata proper. And soon there'll be homework number 2 posted, probably even before homework number 1 is due. Okay. All right. Any last minute questions? Okay. See you next time. Can somebody please stop the video there? Thank you.